What would be the terminal velocity of an 8.20 micrometer diameter piece of basalt silt sinking in water with a density of 1,025 and a viscosity of that? So that's the viscosity of the water. That must be seawater, right? That's the density of seawater. You can't ignore the buoyant force on the particle. And of course, the reason is that the force of gravity, the buoyant force will be actually 1/3 of the force of gravity acting on this, right? Because what the density of salt water is about 1/3 of that, a little more than 1/3, right? The radius of this piece is going to be, and of course it's a perfect sphere, right? Is 4.1 times 10 to the minus 6th meters, right? That's just half of this, right? So we're not going to let the diameter get us, right? Okay, so here's this chunk of silt, right? It's falling through the water, right? The force of gravity is straight down on it. And then we're going to have a buoyant force, about 1/3 of that, right? And then we're going to have about 2/3, right? A force, the drag force, right? And by the way, I know it's 1/3 what, because this is like 1/3 of that, right? Okay, so what we can say is the force of gravity equals the buoyant force plus the drag force, the Stokes force, right? So I'm going to say force of gravity is equal to the buoyant force plus the drag force. And then we can just stick numbers in there, formulas in there, right? The force of gravity is, of course, and we've done this before, right, is going to be mass times g. And the mass is the density times the volume, right? Okay. So the force of gravity is density of the basalt, right, times the volume of the basalt times g. And then and that's for the basalt, right? And then that's going to equal the buoyant force, which is the density of the fluid. This is the seawater in this case, right? Times the volume of the fluid displaced, which is the same as the volume of the piece of basalt, due to Archimedes' principle, right? Okay. And then plus this 6 pi nu RV. I don't even know if that's the letter nu. I should know. It's bugging me that I don't. Okay. But not enough that I actually look it up. Okay, so let's just plug numbers in here, right? The basalt is 2920. The volume is 4/3 times pi times 4.1 times 10 to the minus 6th to the 3rd times 9.81. And then that equals, this is the fluid, so the fluid is the salt water, right? 1,025 times 4/3, whoops, times pi times 4.1 times 10 to the minus 6th to the 3rd. Okay, so that's the volume, and then gravity is 9.81. We'll almost have enough room to put this all in here. Okay, and then it's 6 times pi times, where's our viscosity? There it is. 1.72 times 10 to the minus 3rd. Okay, our radius, we need our radius next. 4.1 e minus 6 times, finally, the variable. All right, let's see, do we have it all? Do we have it all? I feel like we do. V, yes. All right, wow. Now, if you look at this, do you see how you're just going to go, this factor right here and this factor are the same, that factor and that factor are the same, if I make that look like a 9, right? Do you see that there's like some sense that I could like subtract densities here or something like that? Yeah, I really could. Okay, so I'm gonna solve for this V. Are we ready for this? So I go 2920 times 4 divided by 3 times pi times 4.1 e minus 6 raised to the 3rd power times 9.81. Oh, whoops. I always do that. I forget. All right. Times 9.81. Okay. Minus 1025 times 4 divided by 3 times pi times 4.1 e minus 6 raised to the third right arrow times 9.81. I'm just not used to this new OS. All right, okay, so now I've got what equals this term. If I hit enter, I hope. There we go, okay. And now I'm going to divide by 6, divide by pi, divide by 1.72 e minus 3, divide by 4.1 e minus 6, and hopefully I haven't mashed a number here. Did I get the right? Yeah! All right, so my velocity ends up being equals 4.037 times 10 to the minus 5th meters per second. Well, that would take all day for it to settle out, right? And this is a fairly large piece of basalt, right? We can make basalt a lot smaller than that. Okay, so we got the right answer there. And then it says, what time would it take in minutes and seconds to settle in a test tube that is 5.4 centimeters tall? Let's figure out the seconds, right? So time is just distance divided by the velocity, right? So 0.054 divided by 4.037 times 10 to the minus 5th. This will be a lot of seconds. 0.054 divided by that thing. This is equal to 1337 times 0.48. I'm in scientific notation mode, so I'm trying to be sure. This is seconds, right? We want minutes and seconds, so let's divide by 60. So I get 22.29 minutes. Right, so then the question is, how do you turn, this is like decimal minutes, right? How do you figure out how many seconds it is? I'm going to subtract 22 from that. Whoops. And I get the remainder is 0.2914 minutes, multiplied by 60 to get seconds. There is, by the way, a conversion. It's 17.48 seconds, right? I think we can deal with that, right? So it's 22 minutes, 17.48 seconds, right? 22 minutes, that's too long to wait, right? So what they do is they use centrifuges. I'll be sure to do that because these are really boring problems. The centrifuge is like the only bright glimmer of hope, right? It would take a long time for these to settle overnight, or we can put it in a centrifuge. Notice that the gravity is over here on the side that makes these bigger, right? And so if we can get 1,000 times the gravity, it'll settle out in 1,000th the time. All right. The basalt. It's really just, it's like one step harder than when we ignore the buoyancy. And the reason that if this is falling through air, we can ignore this buoyant force is that this buoyant force would be roughly 1/1000th, or 1/3000th the force of gravity because of the density relationship there.